Okay, I would now like to continue our discussions of an observational overview of active galactic nuclei. And today we will be talking about the Broad Line Region, which is often abbreviated as BLR. So we will go back first to sort of set the scale to our AGN powers of 10. In the last lecture, we talked about the black hole region, where much of the X-ray emission is produced. We then also talked some about the accretion disk and the ultraviolet optical continuum emission region. And today we're going to move out a little bit further out to the Broad Line region, which has scales of order 100 to 1,000 gravitational radii in round numbers. The corresponding orbital timescales are of order years, 1 year, 11 years, 31 years here. And the physical size scale for a billion solar mass black hole is of order many light days. So you're getting out to a significantly larger region than anything we've focused on thus far. The Broad Line region you can see is shown here, being pictured as a kind of equatorial wind-like structure with different emission lines being emitted as labeled in different locations, and we'll talk about where that kind of thinking comes from. And then just to connect this to larger scales, here is a 10 times larger scale going from 1,000 to 10,000 gravitational radii. The Broad Line region is down in here, and as we will see, it likely has relevant connections with an obscuring torus, with other outflows, with the narrow line region, and so on. Okay, so that's how it sort of sets the scale. Now, there have been many ideas about the nature of the Broad Line region over the years. In early days, many people envisioned the Broad Line region as a configuration of clouds present in the inner region of the active galactic nucleus. Other people proposed that instead of there being just clouds, there may be bloated stars. If you go back to this diagram, remember these gray dots are representing the location of stars. You plausibly expect on these size scales there be a significant number of stars. And so perhaps these stars, if they were radiated by the brilliant central source, can become bloated up, can have outflowing material off of them. Maybe that has something to do with the Broad Line region. Other people propose that the Broad Line region is a kind of inflow, that material flowing inward that perhaps ultimately is responsible for feeding the supermassive black hole can be irradiated, and maybe that's the Broad Line region. Other people thought, well, maybe the accretion disk itself to some significant degree can serve as the Broad Line region. And then still others have thought of the Broad Line region as a kind of outflowing wind, okay, that again, is irradiated by the brilliant central source and thereby produces the emission line. So those are a selection of ideas about the nature of the Broad Line region. And an astronomical wag long ago sort of summarized the possible motions of the Broad Line region as being either in, like an inflow, out, like an outflowing wind, round, like going round and around in an accretion disk, or about, which is sort of the general less organized motions that clouds or bloated stars may follow. So that's a sort of concise way to summarize the possible dynamical motions of the material in the Broad Line region. Okay, so what I'd like to do now is to just start by talking a little bit about the overall basics of the emission lines that we see from active galactic nuclei, defining very clearly what is meant observationally by the Broad Line region before we start talking about the detailed nature of the Broad Line region. So, as you will recall, active galactic nuclei generally show strong optical and ultraviolet emission lines. You can see them here: H alpha, O3, magnesium 2, semi-forbidden carbon 3, carbon 4, Lyman alpha, and many other weaker lines. Okay, and if you kind of subtract out the underlying continuum and zoom in, as is done in this panel, you can see there are many lines. In fact, if you consider all of these weak lines, look at for example, all of this iron 2 and iron 3 emission running throughout much of the spectrum, and the many other weak lines that are present, it's actually fairly challenging to find any part of the spectrum where you have pure underlying continuum where there isn't some degree of line emission. Now, it may be very weak in places and stronger in others, but it's very common across almost the entire AGN spectrum, running from the optical through to the ultraviolet. Another point I want to sort of emphasize is that this line emission is common. Here, for example, is a quite nice plot where they have taken a bunch of observed Sloan spectra and ordered them by Redshift, okay? And so you can see here the bright lines, which again move toward the red as you go down to higher redshift. Here's H alpha, H beta, magnesium 2, some iron line complexes, carbon 3, carbon 4, Lyman alpha, oxygen 6, and so on. And this plot, concisely summarizes the results from, in this case, 326,886 Sloan Digital Sky Survey quasars. And so you can see this emission line, this line emission is very common for AGNs in general, spanning a broad range of cosmic time. In fact, almost all of cosmic time, you see these active galactic nuclei, and they often have strong line emission. Okay, so these lines are common. Furthermore, I also just want to mention in passing that these lines, while they're often referred to as being an optical and ultraviolet phenomenon, are certainly not only present there. I will here just show you one example of the same types of emission lines, again, likely being from this broad line region, in this case, being observed in the infrared. In this case here, you are seeing Gaussian profile fits to the Passion alpha line, which is the 4-3 transition of hydrogen out at 18,756 angstroms. And so this line emission is also certainly seen out in the infrared. And in fact, there's much to recommend infrared studies of these lines, for example, in obscured systems. And so don't think of these lines as purely restricted to the optical and ultraviolet, although that's commonly where they're talked about the most. Okay, so that's sort of shows that these lines are broadly present across the AGN spectrum. And these lines are also remarkably observed over a wide range of luminosities. These plots here show normalized composite spectra ordered by luminosity. In this case, the luminosity is being measured at 1,450 angstroms. And over an incredibly broad range of luminosities, here spanning a little bit more than 5 orders of magnitude in luminosity, you can see that AGN spectra show the same basic lines being present. Again, over a range of 100,000, and that's a remarkable thing. Over here in this panel on the right, you can see the same basic plot as over here, except here they've limited the scale of the y-axis so that you can see the weaker lines. And even the weaker lines have good similarity over this enormous range of luminosity. So that's another remarkable point. The spectra are rather similar over a very wide range of luminosities. And that's true here, running from, in this case, 1,000 to 2,000 angstroms. And if you also go out to longer wavelengths, as shown here, this is 2,000 to more than 5,000 angstroms, the same thing basically holds. Again, there's a general similarity of what emission lines are present over an enormous range of luminosities, which is a remarkable thing. Interestingly, I will point out here in passing that you can see that the emission lines, while they're almost always present, they do, interestingly, their equivalent widths drop with luminosity. As you go to higher luminosity, the line emission compared to the continuum in general gets weaker. And that's an interesting result that I'll say some more about later on in this talk. But for now, just you can see that these lines are present over an enormous range of luminosities, and take that for what it is for now. So I have then a couple of points to make about these lines. I want to define very clearly what is meant by broad lines from the broad line region and narrow lines from the narrow line region. So if you look at these lines you see in an AGN spectrum, and I'm going to focus on this particular very high signal-to-noise spectrum of a nearby representative active galaxy when discussing this, the lines break up into broad lines that have very large widths. Look at H alpha here, look at this substantial width to it, and H beta, look at this substantial width to it. And those are much broader than, by contrast, this forbidden oxygen 3 line, which is much, much narrower, okay, as you can see there. Sort of quantify that, the broad lines have Doppler widths of like 1,000 to 25,000 kilometers per second. And the narrow lines have Doppler widths typically less than about 900 kilometers per second. Now, 900 kilometers per second is still impressively fast compared to anything that we experience, around the Earth. But those are, again, much narrower, much lower velocity compared to the broad lines, at least. Also, we observe that these broad lines vary often quite rapidly on timescales down to days. So the broad component of this line and the broad component of this line are known to be variable on rapid timescales, whereas the narrow line here, oxygen 3, does not vary rapidly and only varies quite mildly over many year timescales. So that's another hint that there's something distinct going on between the broad lines, which are varying on rapid timescales, and the narrow lines, which are not. Another point which I just want to highlight here is that the many of the emission lines have a composite nature to them. Look at H beta here. You have this clear broad component to it, and then you have this narrow line component spike sitting up here. And similarly for H alpha here. So some of these lines have both a broad line component and a narrow line component. And when you want to study, for example, the broad line emission of H beta, you have to carefully subtract out that narrow line contribution. Or alternatively, you can just look at the variable component of H beta, and that naturally tends to remove the narrow line emission. That's another way to go about this. And broadly the same for H alpha there. Okay. So then, regarding what we can infer about the gas producing these lines, well, one very basic thing we can infer is that the broad lines are arising in, first of all, photoionized gas. So the gas making these lines is producing these lines not because it's so hot that it's collisionally ionizing itself. The gas has a brilliant radiation source shining upon it, and that is what's causing the ionization that ultimately leads to the line production. This is photoionization-driven line production. And that's very important, just to have straight. And you can also infer the characteristic density of the gas producing the broad lines. For example, you can utilize the strengths of certain density sensitive lines, like for example forbidden O3. Forbidden O3, of course, having a longer transition time, will tend to be collisionally disturbed if the gas density is too high. And so the fact that we only see narrow O3 and do not see any broad contribution to O3, even down here at the base of the profile, there's not much suggestion of a broad component of O3. What is there? That's sitting on top of the base remaining from H beta there. But the O3 line is intrinsically seems to be narrow, tells you, well, that there can't be a lot of low density gas that is moving at very high velocities, because if there were, you would see some broad O3 emission, which you do not see. Similarly, we can utilize the semi-forbidden carbon-3 transition to place an upper bound, because we often do observe carbon-3 to be broad, and so that tells you that the density can't be too much more than around 10 to the 11, otherwise that carbon-3 wouldn't be surviving. So we can deduce just from very basic considerations a reasonable density range for this gas, between about 10 to the 9 and 10 to the 11 particles per cubic centimeter. Okay. Whereas the narrow line region gas, based upon similar considerations, is deduced to have a much lower density of order like 10 to the 3 particles per cubic centimeter as a sort of characteristic round number. So the gas producing these lines has a much lower density than the gas producing the broad components of H beta and H alpha. And today we will be focusing on these broad lines, just trying to be very clear and explicit here. Okay. Because the gas producing the broad lines is photoionized, it actually has a relatively low temperature. When you work out the needed temperature of the gas to produce the lines that we observe, the characteristic gas temperature is of order 10,000 Kelvin. So it's not amazingly hot, somewhat hotter than the sun, but not crazy hot by any means. And then, as I've already alluded to, the broad lines are thought to come from this broad line region. The narrow lines are thought to come from this narrow line region. And today we're going to focus on these lines. So that's laying things out very clearly and explicitly. And one other point I want to make then is that you, of course, use these AGN emission lines, first and foremost, perhaps, just to measure redshifts for these active galaxies. You have to be able to measure the redshift to be able to deduce how far away the object is, to learn how luminous it is. So that's a basic starting point to understanding these systems. And interestingly, we find that different emission lines serve better than others in terms of measuring the redshift in a reliable way. So what's being shown in this table from this paper by Shen et al. Is a comparison of the measured redshift measured from a particular line, as labeled over here in this axis, as compared to the redshift deduced from calcium-2, which is a stellar absorption line that gives the best possible systemic redshift that we think is actually representing the actual systemic redshift of the system. And if you carefully remove known luminosity-dependent trends for the various emission lines, and you can read about the details in this paper. Well, for example, if you use this O3 line, you can get the typical redshift measured to with an intrinsic scatter of 50 or so kilometers per second. And, the typical numbers here for O2 and O3 range from, again, around 50 up to somewhat above 60 kilometers per second. So that's the best way to get the redshift from using these narrow lines. And you can kind of understand that. These are very narrow, quite peaked up lines, so it gives you a good way of grabbing on to the redshift and measuring quite reliably. And moreover, these lines don't seem to suffer much intrinsic shifting compared to the underlying systemic velocity, which is not always the case, as we will see. If you in contrast look at the broad lines, well, H beta, for example, isn't as good. You can get H beta redshifts typically only to about 400 kilometers per second or so. And then if you go up to sort of restream ultraviolet lines, you have to switch over to here to what I've boxed here. And you can see you typically with these lines, even after removing known luminosity dependent trends, can typically only get redshifts to within a couple hundred, or for example, for carbon-4, even much worse still, in this case about around 400, or for silicon-4 only around 500 kilometers per second. And so that's sort of the quality of the redshifts that you can get from reasonably high quality spectra. Now again, there are different recipes for removing other trends to get even better redshifts, but this is sort of getting down to around the limit as to how well one can do. So if you want to get redshifts, you should, if possible, focus on these narrow lines because they give you by far the best measurements of the system redshift. So that's one point of utility for these lines, just getting redshifts. Okay. Now, much more could be said about that, but I need to move along. And so I would now like to talk about the basic broadline region properties. Now, I've already said a few words about these just now, telling you the Doppler widths, telling you that they vary on short time scales, giving you characteristic densities, giving you a characteristic temperature. But there are more important things to be said that can be deduced pretty straightforwardly from measurements. Another point one can make is that the observed motions of the gas in the BLR are not thermal motions. The widths of the lines are not broad because the gas is so hot that thermal motions lead to the broadening. In fact, for the known temperature of around 10,000 Kelvin, you only expect typical thermal velocities of order 10 kilometers per second, 20 kilometers per second or so. And so the motions that we observe, which again are often thousands of kilometers per second, are instead supersonic bulk motions. The gas in there is moving in a bulk flow of some kind, And that is leading to the widths of the lines. Okay, so it's supersonic bulk motions of the gas. It's not thermal motions of the gas. Furthermore, the large Doppler widths of the broad lines, thousands of kilometers per second, indicate that they arise deep in the gravitational potential well of the system, down close to the supermassive black hole. I'll quantify that more later on in the talk. And thus, you generally only see these broad lines, at least straightforwardly, in the type 1 AGN system. So if we go back to our little unification model that I've only alluded to a couple of times before, remember there are type 1 systems where you are looking in a more pole-on manner, and you can look down into the nuclear regions where the high velocity gas is present. Here the broad line region is labeled as being down in here, inside this equatorial obscuring material. In contrast, for the Seyfert 2 objects, the objects viewed in a more equatorial or edge-on manner, well, there, this obscuring material lies along the line of sight, and that generally prevents you from getting a nice, straightforward, direct view of the broad line region. Now, there are further complexities there to be sure. We'll talk about some of these more later on when we talked about the unified model, but that's, to first order, the nature of how things go. You generally see these broad lines in the type 1 systems and not so much in the type 2 systems. And in fact, the definition of type 1 and type 2 systems originally, goes back to the widths of the Balmer lines. And so almost by construction, you will only see the broad lines in the type 1 AGN systems because that is in fact how they are formally defined. Now we interpret that in retrospect in light of this unified model, but that's the general idea from a direct definitional point of view. Okay, a couple of other points. We can deduce the typical covering factor of the gas in this broad line region, and we deduce that to produce lines with the strengths that are observed, this implies a global covering factor of the broad line region of around 20 to 30%. So if you were down at the nuclear source, down close to where the black hole is and looking out at the sky, about 20 to 30% of the sky would have to be covered by this broad line region gas to be able to produce lines as strong as we observe them to be. Okay, and more about that later on. Furthermore, you can also deduce basic points about the metallicity of the gas. And this is often done based upon looking at line ratios, looking at observed line ratios, and then comparing them to photoionization modeling of line ratios. And some line ratios are sensitive to the metallicity. And in fact, if you utilize those types of arguments, you find that the metallicity generally appears to be about 3 to 10 times supersolar. And that's what's being shown down here in these plots, for example, where here again you have metallicity, in this case shown versus black hole mass and versus luminosity. And you can see there's interesting correlations with these quantities, but leaving those aside, just broadly speaking, you can see, given that this is a logarithmic quantity, the metallicities are around 3 times down here and perhaps up to somewhat more than 10 times solar. And so those are the kind of metallicities that are deduced to be present, broadly speaking, in these active galactic nuclei. And that's down only in the nuclear region, okay? At these luminosities. Here, this particular plot is mostly focused on quasars, but broadly speaking, even for lower luminosity, lower mass systems, well, there you get down to of order solar metallicity at about the lowest. Okay. A couple of other points. So if you look at the profiles of the broad lines, they are usually non-Gaussian. Okay, the line profiles, as shown back here, for example, are not well fit. Once you subtract out the narrow line component, generally they're not well fit with just a simple Gaussian component. You typically need a couple of Gaussian components to be able to statistically fit the line in an acceptable manner, or some people prefer a Gaussian and a Lorentzian combination, and there are debates over which approach is the best, but the lines have profiles that are significantly more complex than just a single Gaussian. In a single source, furthermore, the profiles of different broad lines show diversity. So not all lines in a single source will all be fit by the same broad line model. In general, for example, lines of more highly ionized species tend to be broader. Okay, so there's diversity among the lines in an individual object. Furthermore, some lines, particularly those of high ionization, carbon-4 is a famous example, can show significant blue shifts in the AGN rest frame. And I have an example here to show what I mean by that. So here is, at the bottom panel, a typical Sloan Digital Sky Survey composite spectrum. Okay, and even in this composite spectrum, you can see that if you center up your redshift on, for example, magnesium-2, you can see that carbon-4, generally speaking, seems to be somewhat blue shifted, okay, compared to magnesium-2. To show a much more extreme example, look at this upper panel. This shows the spectrum from Sloan for a single object, this particular quasar, which is one of my best friends among the quasars. And here is the magnesium-2 line, which again, the redshift seems to be pretty good, pretty well agreeing with magnesium-2. But look over here at carbon-4. This object has rather weak emission lines, but you can see there clearly is carbon-4 emission there. But look at the carbon-4 emission. It peaks clearly offset from where the typical carbon-4 emission should be, and also clearly offset from what you would expect compared to the magnesium-2 in the same object. And so the carbon-4 line is highly blue shifted in this system. This again is admittedly an extreme system. In this case, the carbon-4 is blue shifted by about 9,300 kilometers per second, and that corresponds to about 21 million miles per hour. And so something dramatic is going on in the carbon-4 producing region of this quasar to cause it to be highly blue shifted compared to, well, other emission lines in the same source and compared to what you would expect from composite quasar spectra. So these blue shifts can sometimes be quite remarkable and, stand out very obviously. Furthermore, another point I want to make is that in many cases, the line profiles have additional structure to them beyond even 2 to 3 Gaussian components. There's additional complexity. There can be bumps on the line profiles, humps, broad humps on the profiles, asymmetric wings. One notable extreme example, which are fairly rare but are very interesting to study, are the so-called double-peaked BLR lines. And here are a couple of spectra of double-peaked BLR lines. This one over here is particularly impressive, where again you have some narrow component emission. But look at the broad line here. You have this broad hump type structure, which then goes down here, and then it goes back up over here, considering just the underlying broad component. It goes back up there. So this thing appears to have a sort of characteristic double-peaked profile. That kind of double-peaked profile is characteristic of rotating disks, as you will remember, for example, from our discussion of the iron K alpha line in the previous lecture. And this basic phenomenon is also seen in other systems with disks, cataclysmic variable systems in our galaxy, for example. And so the fact that you sometimes see these double-peaked BLR lines suggests that, well, at least sometimes, perhaps some of the broad line region emission is from a disk, or at least some disk-like structure. And these double-peaked BLR lines, I will just mention in passing, can show complex variability patterns over many-year timescales, showing all sorts of interesting, fascinating behavior. And people who like these systems have often been monitoring them for many decades, trying to understand what's going on in them. There's much more that could be said about them, but that's all I can say for now. So then going to the broad line profiles, a few more points to say about them. Well, unfortunately, modeling the profiles in most cases, leaving aside these double peak systems, which again are rare, and in these cases the modeling of the profiles can be very physically revealing. But for your typical single peaked line, unfortunately modeling the profiles usually does not strongly constrain how the gas is moving. Is it going in or out or round or about? There are modeling degeneracies, so you usually can't distinguish those possibilities just from the profiles themselves. There are counterexamples, but that's generally the case. However, constraints upon microstructure in the line profiles has been very revealing. So here, what people have done is they have gone and obtained high spectral resolution, very high signal-to-noise spectra of nearby active galaxies. And here, for example, is the H-alpha and H-beta line for a nearby active galaxy measured at high spectral resolution with very high signal-to-noise. And you find that the profiles, when measured at high resolution, are quite smooth. This is interesting because it constrains the number of discrete, we will refer to them as clouds or emitting objects, that are required to be producing the line profiles. If you had a line that was made by just a small number of clouds, say 5 clouds in the broad line region, well, then you would expect that this profile would have significant microstructure to it or quantization to it because the number of emitting sources is small, so you'd get little step function behavior in the line profile. But that is not observed. And people have, again, done modeling of this type to set constraints upon the number of any discrete clouds in the broad line region, and you find the number must be very large, more than 1 million or even larger. This indicates that, in fact, the broad line region may not be clouds at all, that there may not be discrete emitting objects that you can identify as clouds producing the line emission, but rather there may be a continuous flow of material that is responsible for producing the observed broad emission lines, okay, which is an important finding. This sort of pushes you in the direction, again, of a continuous flow model instead of distinct clouds being responsible for the broad line region. Furthermore, there are fascinating and important non-random object-to-object differences in the properties of the lines from the broad line region and from the other, and also including the other emission lines as well, from the narrow line region, for example. And that's what I write down here, that these fascinating object-to-object differences, which are non-random and important, can connect to the black hole region, to the narrow line region, and to other AGN regions. But they often manifest themselves prominently for the broad line region, so I will talk about them here. And in particular, in the next few slides, I'm going to describe 2 notable examples. One of them I have already shown, at least qualitatively, and this is this luminosity dependence of equivalent width, where, again, while active galaxies show the same basic emission lines over an enormous range of luminosity, the equivalent widths of these lines drop as you go to high luminosity. Okay? This is observed for many emission lines. Carbon-4 is one of the most prominent examples, and this behavior of the equivalent widths dropping as the luminosity increases is broadly referred to as the Baldwin effect, after one of the astronomers who originally noted and emphasized the possible importance of this phenomenon. Now, I will say that, in fact, different lines show a different rate of weakening in equivalent width as the luminosity goes up. This has all been extensively measured and quantified. There's interesting correlations and interrelations there, which you can read about if you're interested. I won't go through all the technical details, but broadly speaking, that is what's seen. And in fact, notably, in some cases, this so-called Baldwin effect behavior, in fact, appears more fundamentally linked to the Eddington ratio than to the luminosity. Now, as you would expect, given that the Eddington ratio was the ratio of the luminosity to the Eddington luminosity, well, the Eddington ratio was going to be strongly correlated with the luminosity itself. So you have to do a kind of partial correlation testing to in fact deduce that the Eddington ratio is the more fundamental quantity, and that seems to be the case for at least carbon-4, for example. So Eddington ratio has some significant role in causing this behavior. There's much more that could be said. It's also likely that the AGN spectral energy distribution, which is responsible for ionizing the gas that makes these lines, has a significant luminosity or Eddington ratio dependence to it. Other people, I've been involved in some of this work, have suggested that thick inner disks may affect the amount of radiation that can ultimately reach the broad line region, and perhaps that's an important driver of the Baldwin effect. And there's many things that could be said about the interpretation of this, but I'm not going to go through all the details here because we have limited time, but that's one important object-to-object differences for active galaxies. Now, there's another one I want to emphasize. This one goes generally by the name of Eigenvector 1. So astronomers have utilized the statistical technique of principal component analysis to investigate the multidimensional space of AGN emission line and other properties. So they take a sample of active galaxies, they measure the emission line properties systematically for all of them. They have a bunch of measurements of line widths and line strengths and blue shifts or red shifts of lines and profile properties of lines. They measure all these quantities as well as they can. They feed this into this principal component analysis technique. And what they essentially then are doing is they are looking within this multidimensional space of AGN emission line properties to define a new coordinate system in which each successive coordinate direction, defined by so-called eigenvectors, explains as much of the remaining variance that is present in the underlying data as possible. So you're looking for these eigenvectors that explain most of the object-to-object variability among active galaxies. And this principal component analysis turns up interesting things. In particular, there is a set of emission line properties, which again go by the name of Eigenvector 1, that vary in a correlated manner. And I'll just sort of show you what's meant by that. So here is an example. This is from this very influential work by Borison and Green, although I will emphasize there were many other papers investigating these issues. And here are examples of the spectra that they obtained in the H beta and O3 region. And you can see that some of these active galaxies, like this one, have these nice prominent broad lines, have this very strong forbidden O3 emission, like this one here and this one here, where in contrast there are other objects, this one here and this one here, that are very different. Where here the O3 emission is much, much weaker, almost hardly visible in these systems, at least in this one. And this one has very strong optical iron 2 emission, causing all of this spectral complexity that you're seeing here, which is not so much present in this system here. So here you have this optical iron 2 emission. And so there's a fundamental difference between objects that are like that and objects that are like that. And again, this is quantified by this principal component analysis approach. And what you find is that once you define this so-called Eigenvector 1, and for now just focus on these top 4 panels, well, you find that most of the object-to-object differences correlate with each other, such that, for example, objects that have strong optical iron 2 emission compared to H beta specifically also tend to have weak O3 emission, also tend to have relatively narrow optical H beta full width half maximum line emission. So the H beta line tends to be narrow. These objects then also tend to have H beta asymmetry tilted toward the blue. Okay, so there's this correlated set of properties that all vary together. And while there is surely object-to-object variance, you can see all the scatter present, there are clear correlations there. And that's very important. That indicates that there's kind of a method to the madness of these quasars, that quasars aren't just random, where you can just pick any set of random line properties with a random number generator and stick them together and you get a plausible quasar. That's not the case. Quasars play by certain rules, and these rules are defined, for example, by this Eigenvector 1, for example. Now, then if you look at the other extreme over on this side, well, then you have weak optical iron 2 emission systems, also having strong O3 and having broader H beta and having red asymmetric H beta. So that's the other extreme of this correlation. And these correlations have been noted in one way or another by many people. And there are different names that are used. For example, people studying the narrow H beta systems, they often homed in on this, found these objects and called them the so-called narrow line Seyfert 1 galaxies, which are also the objects that generally have strong optical iron 2 emission and weak O3 and blue asymmetric H beta. And so people, came across these basic results in a variety of ways, but this sort of eigenvector approach kind of ties these things together in a very efficient and interesting way. Moreover, and I was actually involved in some of this work in the early days, people found that these correlations, which again span here the broad line region, the broad line region, the broad line region, and here the narrow line region, which we haven't even talked about yet, but this is a narrow line region property here. These emission-line correlations actually connect to other AGN regions as well. For example, if you look down in the black hole region, using X-ray measurements, you find that the X-ray properties, in this case, the Rosat photon index. So this is the X-ray spectral shape measured in a very soft X-ray band, which essentially is telling you about the strength in general of that soft X-ray excess component that I talked about in the last lecture. You find that the objects that tend to have very strong soft X-ray excess emission are the same ones that are over here and over here and over here and over here. So the black hole region is also connected to all of this, where the objects over on this side have very strong soft X-ray excess emission, the objects over here much weaker. And so you have here this sort of connection of AGN properties on an enormous range of scales, from black hole region to broad line region to narrow line region. And this, again, is showing you that there is a kind of method to the madness of these active galaxies, that they are all linked together and can be understood the same way that one can understand stars, using the main sequence. This is the same type of idea here for the quasars. Now, this Eigenvector 1, well, you want to then physically understand, what does it mean? Well, many studies of that, utilizing the properties and our physical expectations of how these lines are made, and the X-ray properties are particularly revealing here, all indicate together that this Eigenvector 1 is likely a measure of the Eddington ratio of the system, such that objects that are over here, the narrow line H beta, strong optical iron 2, weak O3, blue asymmetric, strong soft excess systems, are the rapidly accreting supermassive black holes. And at the other end, as you move in this direction, you're moving toward generally lower accretion rates. Now, there's many more complexities there that have been explored in many papers subsequently, but that shows you the essentials of the idea, and you can read additional papers if you want to learn more. But you can see these quasars have structures to them. They're not just random, and one can start to understand them one can sort of put a given quasar in context by relating it back to these quantities, and can thereby come to understand it in context in an effective and efficient manner. Okay, so that's what I had to say about the general broad line region properties. I would like to continue and talk to you about results from reverberation mapping of the broad line region. This has proved a very effective way to understand the broad line region. First of all, just going back to the variability of the BLR lines, the broad lines are observed, as I've said, to vary on short time scales. And they generally vary in an interesting way. They generally are observed to follow the continuum variations, but with a time delay. And a nice example of that is shown down here. This shows the continuum, in this case measured at 5100 angstroms, of this particular active galaxy, Markarian 335. And then here is the emission line light curve for helium-2, and you'll note that the helium-2 emission line light curve has the same basic variability trend to it, but is shifted. It peaks over here, whereas the continuum peaks over there. And if you go to H beta, the shift is even more pronounced. H beta is such that it peaks over here, very obviously shifted from the continuum. So you can see the emission lines are following the continuum of variations, but with this time delay. And this is broadly observed for these active galactic nuclei, although I will point out, and we'll say more about this in a little bit, that there are some notable exceptions to this behavior, which can make this whole enterprise a little bit dangerous sometimes. So if you have these lags being present, well, what can you do with them? Well, these are thought to be due to the light travel time across the broad line region. And so this leads to the idea of so-called BLR reverberation mapping, whereby if you have variations in the continuum down here at a small scale, and these are then being reflected by variations in the emission lines made on a larger scale, say out here somewhere, okay, and down here is the continuum light curve, here is the corresponding H beta line, you can see the time delay there. If you have that time gap or lag being present, well, that tells you something about the physical size, at the least, of the region that is producing the line emission. So you can use time delays to measure the size of the region, at least a first order. You might also hope that if you measure the line profiles even more carefully, you could reveal not only the size of the broad line region, but also its structure. And people have the idea of trying to do that, and indeed are working to do that right now. So here, to sort of lay this out a little bit mathematically, is the kind of formalism that is used. Here, L of t is the measured line flux for a given line from the broad line region. C of t here is the ionizing continuum flux of the system. And I will just mention now and say more about this in a little bit, that the ionizing continuum flux responsible for making a given line is not necessarily the continuum, well, it's almost never the continuum close to the line that is actually being directly observed by the spectroscopy of the line itself. And that's a bit of a challenge, as we will come to in a little bit. And then finally, psi of tau here is a transfer function that encodes information about the broad line region. So the line response is expected to be the convolution over a range of time delays, tau, of the ionizing continuum flux light curve and the transfer function of the broad line region. And what you want out of this whole endeavor is this thing, which tells you about the broad line region, given your measurements of L and of C. That's the idea. That's the game you're trying to play. And so you're trying to deconvolve this thing. Now, for those of you who are familiar with Fourier transforms, you know you could Fourier transform both sides and use Parseval's theorem. Practically, that approach tends not to work so well. And so other approaches are generally used to measure the broadline region size. And I will just say right now, and show you some examples in a minute, that the broadline region size generally is observed using these techniques to have a size ranging from about 1 light day at low luminosities up to more than 1,000 light days for the very highest luminosity systems that have been reverberation mapped. And again, as I mentioned, you could also hope not only to measure the size of the broadline region, but also its structure. And you might attempt to do that by performing velocity resolved reverberation mapping, where you don't just do this deconvolution for the entire line flux integrated, but you break up the line into different velocity components, and you then do this procedure on each velocity slice across the line. And that gives you even more information, which can let you deduce the structure of the broadline region if you have very high quality data, as I'll say more about in a little bit. So that's the overall idea, sort of formalized. That's the kind of game that's being played here. To put this into a little more context, this plot here, which I showed in the previous lecture as well, is just a plot that nicely summarizes the general enterprise of reverberation studies. Now, the reverberation that we're talking about here is, again, reverberation of the broadline region. So the thinking is that you have an ionizing continuum source in the extreme ultraviolet generally, as I'll talk more about soon, shining upon the broad line region gas, causing these emission lines to be produced. That's the optical BLR reverberation mapping. And that's the one we're talking about today. You will remember in the previous lecture, I talked about other approaches using this reverberation mapping approach, where people try to study the corona and watch how the corona in the X-rays affects the reflection of the X-rays off the accretion disk. That's X-ray reverberation mapping, which again I talked about briefly in the last lecture. And then there is also this optical ultraviolet continuum reverberation, where the idea is you have some driving source on small scales that could be reverberating the accretion disk. And I talked about that and some of its challenges in the previous lecture as well. But for now, we'll talk about this one, the optical BLR reverberation mapping. And in fact, this is the first one that was done extensively for active galaxies, with these other ones coming later. And I will mention that also you can do reverberation mapping of dust in the torus to try to understand that. And we'll talk about that in a future lecture. But for now, we're talking about this one now today. So there are some challenges with attempting to perform reverberation mapping of the broad line region. First of all, as I've shown you, you have this kind of convolution equation that you're trying to unwind. That is a challenging procedure. To have a reasonable chance of unwinding that in a robust manner, you must have high quality data, which means this BLR reverberation mapping effort is going to be an expensive one. You need dense, reliable sampling over long time scales of an active galactic nucleus, all with spectroscopy. And you need to try to do that avoiding or minimizing to the greatest extent data gaps. And so you often want to perform these programs at multiple sites, so weather doesn't impose bad data gaps, which can be very destructive when trying to unwind that integral equation. Furthermore, the spectra must have excellent flux calibration, because what you're doing here is you have to have the absolute flux of the line and the absolute flux of the ionizing continuum, okay? So you want to have good flux calibration to be able to do this as reliably as possible. You also find that, unfortunately, the broadline region sometimes does not show clear reverberation behavior. I sort of alluded to this before. You generally see that this sort of phenomenon of the lines following the continuum with a lag generally seems to hold. But once in a while, even in systems that often have shown good reverberation behavior, sometimes they'll go into a strange state where the lines seem to stop reverberating for reasons that are still sometimes mysterious and debated. Sometimes it may be obscuration coming into the system that is stopping this reverberation behavior for a while. So these things can cause great challenges when just an AGN decides, I'm not going to cooperate. I'm not going to show this reverberation behavior that you were hoping for because I'm on holiday. And in fact, these events where reverberation stops are sometimes referred to as BLR holidays, trying to make the best of a bad situation, perhaps. In any case, another point which I want to emphasize, and I've already alluded to, is that unfortunately, in general, for these broadline region reverberation mapping experiments, the continuum that you're actually observing is not the ionizing continuum. And I want to make that very clear. So the ionizing continuum for these BLR lines is out in the extreme ultraviolet, which is generally not observable. And I've sort of given some characteristic numbers here. If you define this chi parameter to be the ionization potential, well, for high ionization lines, the ionizing potential of those is sort of 40 to 50 electron volts. For intermediate ionization lines, it's like 20 to 40 electron volts. And for low ionization lines, you're typically down at less than 20 electron volts. Now, all of these are generally well above the actual continuum that you're measuring. The ionizing continuum is up here, again, at tens of electron volts. It's up there. Whereas what you're typically measuring is line emission down here in the optical near UV, going out to perhaps to Lyman alpha. And even Lyman alpha Well, its corresponding energy to be compared with these is 10.2 electron volts. So even with Lyman alpha, you're not even very close to the ionizing continuum responsible for making many of these lines. And so that's a real challenge because the ionizing continuum may be varying in ways that are different than how the actual observed continuum is varying. And so that can lead to a lot of confusion. But nevertheless, the observed continuum often seems to serve reasonably well as a predictor of the ionizing continuum, which makes this whole thing actually work. Okay, so those are some of the challenges. Now, not to be too negative, but those should always be borne in mind. But despite those challenges, many people have, with good success now, been performing these reverberation mapping experiments. And in fact, there's a whole industry of people all around the world doing these kind of reverberation mapping experiments. Here's a nice compilation compiled by my colleague Pudou, showing on a map of the world where many of the reverberation mapping experiments are sort of centered in terms of where the data are being gathered and so on. There are many places all around the world. There are also observatories in space. Hubble Space Telescope has been used for this extensively. And here is a list of some of the reverberation mapping programs. I can't go through each one, but I'll just sort of give you some of the general trends. So there are some experiments that are taking bright, nearby active galaxies and trying to monitor them very intensively to get very high quality data, to really understand the subtle details of the Broad Line region, and to in some cases, try to do this velocity resolved reverberation mapping. There are other efforts that focus on extreme examples of active galactic nuclei. Here is a very successful project that has looked at so-called super Eddington accreting massive black holes, looking at systems that are accreting at very high Eddington ratios and seeing how they differ. There are people that are monitoring AGNs with H-beta asymmetry, and that's of considerable interest. There are people conducting very long-term reverberation mapping programs, trying to get the lags for the most luminous quasars in the universe. These are expected to have very long lags, and these experiments can run for decades. And then there also are so-called industrial scale reverberation mapping programs that are trying to mitigate this very large expense of reverberation mapping. Here, the idea is you use a spectrograph that has many fibers, and you go to a wide field of sky, and you use a spectrograph that can access that wide field effectively. You put many fibers on the sky, and you try to reverberation map hundreds of objects all at once. And that has been done now with some success by the Sloan Digital Sky Survey Reverberation Mapping Project and by the Australian Dark Energy Survey Reverberation Mapping Project. There's some very interesting results coming from those. So this gives you a sense of the types of things that are being done, broadly in the reverberation mapping industry. Lots of interesting things being done. And many BLR lines have now been reverberation mapped. Here is this same plot that I showed you previously, but now I have arrows pointing out the lines where reverberation mapping has been done, often with good success. You can see with people of reverberation mapped Lyman alpha, silicon 4, carbon 4, carbon 3, magnesium 2. This optical iron 2 emission has even been reverberation mapped in some cases. H beta, H alpha, and so on. Lots of lines have now been reverberation mapped. So this is a growing, successful industry. So I'll say a few results on these. First, I want to show you the dependence of the emission region size deduced from those lags for H beta and also for carbon 4. Okay, and I want to show you those. So here is the measured size of the H beta emitting broad line region, okay, plotted versus luminosity. So this is the broad line region size versus luminosity here. Here again is another paper which uses some of the same data, but with some important technical improvements, showing the H beta broadline region size versus luminosity. And you can see that there's a clear correlation there. Okay, more luminous systems have bigger broadline regions. And notably, the broadline region radius is found to scale. such that the radius of the broad line region that's producing H beta, so that component of the broad line region, that'll be important as I talk about later, roughly scales as the luminosity to the 0.5 to the 0.7 power, okay, broadly speaking. That slope is about as expected if all AGNs have similar ionization parameters and densities in their broadline regions, which you would expect a scaling that goes as R is proportional to L to the 0.5. So your kind of basic theoretical expectation seems to be matched well by the data. And that's always very pleasing when something like that actually works out. So that's H beta. Here is the similar plot, in this case for carbon-4. So again, here you have carbon-4 lag, okay, for all significant lags measured, and then for a sample with very high quality measured lags in this bottom panel, spanning a very broad range of luminosities coming from multiple different experiments combined together. And you can see there is pretty clearly a carbon-4 luminosity relation as well, although this relation has more scatter. Anyway, so there's a nice relation there for carbon-4. And interestingly, you find that for a given luminosity, the carbon-4 line has a smaller physical emitting region size than does H beta, telling you that they actually are coming from physically different regions in the AGN structure. I'll say more about that soon. Furthermore, another very interesting result is that the dependence upon luminosity is likely not the only dependence here. It's not as simple as that. There are other factors that come into play in setting the size of the broadline region as well. And that has been shown, for example, by this group of people that are attempting to reverberation map these super Eddington accreting sources that I've alluded to. And so here are measurements they have made and have combined with literature results of the H beta region size versus luminosity for the general AGN population up here, which is fitted by this dotted line, and for their so-called super Eddington accreting sample shown by this dashed line down here. And you can see the relations are pretty clearly offset from each other. Okay, this indicates that luminosity is not the only factor setting the size of the broadline region, but that Eddington ratio also matters. And here is their nice plot showing that here is this sort of difference in the region size for H beta plotted versus Eddington ratio. And you can see that the general relation that we've talked about previously, the dotted line here, works pretty well at low Eddington ratios. But when you go up to high Eddington ratios, there's a clear offset there. And the broadline region size gets to be smaller, okay, at a given luminosity as you go up to high Eddington ratios, which is plausibly what you would expect from virial considerations and so on. So that's very interesting. That's another important finding. So we have sizes for the broadline region, and we have dependencies upon luminosity and upon Eddington ratio, so that let you tell how big the broadline region should be for a given object. That's all very interesting and important. Furthermore, reverberation mapping has revealed that and I've already alluded to this, that the line emitting regions are stratified. And so what's meant by that is that the highest ionization emission lines generally respond most rapidly to continuum changes. And as you go downward in ionization, the reverberation times are generally getting longer and longer, indicating ionization stratification. That is shown nicely here in these recent very detailed reverberation experiments for a reverberation experiment for a very well-studied AGN. So helium-2, which is a very high ionization line, is very small. And this basically shows the distribution of delay timescales coming from unwinding that integral equation I showed you with sophisticated mathematical techniques, and that's being done for different lines. And then these red vertical lines show the kind of median size for the overall distribution. Helium-2 has a very small size because it's a very high ionization line. Carbon-4, somewhat lower ionization, is somewhat larger. H-beta, lower ionization still, is larger still. And so that's this ionization stratification that I'm referring to. So what that translates into, going back to this little schematic order of magnitude, sort of power of 10 diagram, is again, helium-2 is made on very small size scales, carbon-4 and silicon-4 on somewhat larger size scales, lower ionization lines like H beta, magnesium 2, and so on larger size scales still. Okay, so you have stratification of the broad line region. Not all the lines are coming from a single structure. They're spread out where they're coming from, and I'll say more about that later on. Now, another important point is that if you look at the lag and you look at how the lag relates to, for example, the line width, you find that the lag scales as the line width to the minus 0.5 power. And that's what you would expect for virialized gas dominated by the gravitational potential of the central source. And to illustrate that, I just here have a quick and dirty derivation of that, where if you just take the virial theorem for gravity, the kinetic energy is minus 1/2 the potential, and you put in your simple equation for kinetic energy and for potential energy, you then find that the velocity width of the line should be proportional to 1 divided by the radius to the 1/2 power in the denominator. Okay. And so then the velocity should be proportional to 1 divided by c times the lag, that's r, to the 1/2 power, or thus proportional to 1 divided by the lag to the 1/2 power. So that's the predicted scaling you expect for virialized motions in the broad line region. And that is in fact what is observed. Here is, in this case, H beta and other lines being shown, and they follow a general relation in agreement with the virial expectation. So it appears this gas is indeed virialized, at least in this particular system. Now, of course, one must worry that this may not always be the case, and in particular, when you are studying systems with very high Eddington ratios, well then almost by definition, radiation pressure is going to become important in those systems, and so for those systems, things may get more complicated, and one has to be quite careful. But broadly speaking, one often observes evidence for virialized motions of the gas in the broadline region, which supports the idea that you might be able to, for example, deduce black hole masses for these systems. Okay, come to the black hole masses soon, in fact. Now, a couple of other points. Another important finding is the phenomenon of so-called BLR breathing. Here, people find that the H beta broadline region is often observed to exhibit so-called breathing behavior over year time scales. And what's meant by that? Well, the broadline region emitting H beta, that part of the broadline region appears to become larger as a source varies to high luminosities, and then becomes smaller as that source declines to lower luminosities. And here are some plots illustrating that general behavior. Here it is for this system NGC 5548. And basically you can see as the mean flux goes up, it appears that the time lag, which is telling you, again, the characteristic size of the broadline region, gets bigger. Okay, so this is this breathing phenomenon where the broadline region appears to be expanding and contracting following the flux or the luminosity of the system. Here is another similar result, in this case from the Sloan Digital Sky Survey Reverberation Mapping Project for one particular system. Here you can see H alpha and especially H beta showing this same type of behavior, where here what's being plotted is changes in the full width half maximum of the line compared to the flux of the continuum. You see this characteristic breathing type behavior. Okay, so what does this mean? Well, we don't think that this breathing implies that the broadline region gas itself is somehow physically expanding and contracting under such breathing. We don't think that's what's going on, where the broadline region mechanically is expanding and contracting. The timescales are just not feasible for that. Rather, the thinking, and this is kind of illustrated in this plot that I showed you back here, is in fact we think there is gas everywhere in this extended broadline region. There's gas filling this entire region in general. And what changes is not the mechanical size of the broadline region with the gas physically moving in and out, but instead what is changing is the distance from the continuum source where conditions are optimal for line emission. This idea broadly is referred to as the local optimally emitting cloud model. Sometimes this acronym, different words are attributed to that acronym, but I shall not utter them here. And that's the basic idea. Now, what this then implies is the total reservoir of gas in this line emitting region is actually much larger than the gas that is actually producing a given line. Okay, and in fact, one can infer that the total reservoir of gas present is, broadly something like 1,000 to 10,000 solar masses worth of gas, although only a small fraction of this gas, perhaps less than 1% for many lines, is actually radiating line emission efficiently at any given time. Okay, so there's a large reservoir of gas there, and as the luminosity goes up and down, the conditions in that gas that are optimal for the production of lines moves in and out as the luminosity goes up and down. And that's the cause of this breathing behavior. And that's why this breathing behavior is physically important and revealing. Now, all that being said, things aren't perhaps quite as simple as that, because if you study other lines, this breathing behavior is best observed for H beta. But if you look at other lines, well, some of them, in fact, don't seem to breathe very much, and some of them may even show anti-breathing behavior. And that causes additional complexities. I won't go into them here. You can read about them in this paper, for example, if you're interested. And there's other good papers on this subject as well. Okay, so now I want to get to this topic of estimating black hole masses based on reverberation mapping. So as we've already talked about, the gas appears to be virialized. And so if that is indeed the case, one might hope to be able to measure black hole masses following the virial theorem. Using these same basic arguments that I show here, you can show that the mass of the black hole is equal to a F factor, which, as we will see, sort of includes the complexities of the broad line region and the inclination, times the lag, times the speed of light, so that's the characteristic size, times the velocity width of the line squared divided by the gravitational constant. So that's the idea. We can measure this pretty well from the spectra. We can measure this from the reverberation mapping. And, of course, we know the G. And so what is more complicated is getting this F factor, which again is a kind of fudge factor that includes the BLR geometry and the inclination and so on in it. Now, people have compared reverberation measured masses with other mass estimation methods for nearby systems that people can study very well. And generally, they indicate an average value of this F factor of like 4 to 5. Okay? And so if you use that kind of a value, and this can also be measured with this velocity resolved reverberation mapping technique that I'll talk about a little bit later. But in any case, if you use that kind of an approach, you find that the masses measured appear to be accurate to within about a factor of 3 or so, at least when H beta is used. For other lines, it's often not as good. But for H beta, if you have H beta available and you reverberation map that, you can actually likely measure the black hole mass to within about a factor of 3 or so, which is not bad. Now, people then have used these approaches to now measure the masses for large numbers of black holes. Here is a nice plot showing some of the results recently from the Sloan Digital Sky Survey Reverberation Mapping Project, where again, here people have multiplex reverberation mapping and a reverberation mapping hundreds of objects all simultaneously using a wide field spectrograph that can cover many objects up on the sky with multiple fibers, okay? And over now a wide range of redshift, using multiple lines, people have measured black hole masses directly, spanning about 85% of cosmic time and reaching through to the peak era of supermassive black hole growth. So that's quite nice that this can be done. And again, there are also many excellent reverberation mapping results in the local universe. This part, the sort of redshift 0 region, has also been populated very extensively by many of those other very valuable reverberation experiments. And you can see the black hole masses that are deduced range between about 10 to the 7 to 10 to the 8 to even somewhat more than 10 to the 9 solar masses in the most extreme cases. Those are the kinds of masses that are being found. Okay. Now, a couple more things to say. So once you've done this reverberation mapping technique, and if you indeed believe that the material making the lines is virialized, well, then you can try to take this another step forward. And this gets to be a little perilous, but people often do it. What they do is they combine the radius of the broad line region luminosity relation that says that once you measure the luminosity, you can predict what the radius will be, and you can combine that with a measured line width to estimate a single epoch mask, where you don't have to reverberation map the object. You just measure the luminosity, which apparently tells you this. You measure the line width, and you have a little equation that lets you spit out what the black hole mass should be. Okay, this is the equation here, again, for H beta. Similar relations exist for magnesium-2 and carbon-4. Here are some recently derived relations of this type, where again, for a given line of interest, which can be H beta, magnesium-2, or carbon-4, you plug in these properties with these coefficients, and you have a nifty little equation that'll spit you out a black hole mass. Okay, so that's the idea. It sounds great in principle. In practice, it has its ups and downs. These approaches, do have the great benefit of allowing quick estimates of black hole masses for large AGN samples, but their accuracy is no better than a factor of several. If you have to do this and you have access to the H beta line or magnesium-2, those are the best lines to use. This gets to be a much more hairy procedure if one is using carbon-4, but people are attempting to, rehabilitate carbon-4 as a single epoch mass estimator as well. But in any case, that's what people are trying to do. Another challenge is that you have to very carefully characterize the line widths. You have to be sure to measure them in the same way that the people that derived the equation in the first place measured the corresponding line. Otherwise, you're putting in something that is different than what the people actually used to make the equation in the first place, and that can cause problems. So you have to be very careful and do everything in a very consistent way. And if you do all that well, then I would say statistical use of such single epoch masses in large samples is probably okay for drawing broad general conclusions. But if you start focusing in too much on individual objects, then mass estimates may be unreliable, particularly if you're using a line like carbon-4, or if you're considering a system where the Eddington ratio may be very high, and so the gas may not be fully virialized. Then things can get very dangerous. So these should be used, but only with suitable introspection and caution and attention to the details of how these relations were derived and where they are indeed applicable. Okay, the final thing I will say regarding this reverberation mapping goes to this idea of velocity resolved reverberation mapping, where again, here you don't just measure the integrated line flux and how that varies over time, but you also measure the full line profile and measure the flux in different segments of the line profile and look at how all of that varies over time in an attempt to deduce the underlying structure of the broad line region directly. Now, this is even more challenging than the reverberation mapping efforts with integrated line flux, but this has made very good progress in recent years. And to sort of show you how this game is played, well, what people do is they work out these so-called velocity delay maps for different cases of what the broad line region might be like. For infall, for a less extended BLR, for infall with a more extended BLR, for an inclined Keplerian disk, for a thick spherical shell, and so on. And I'm just going to give you one example. Let's take this simple example up here of infall. Okay, so the idea here then is that if you have infall going on, well then over, so there the material's flowing inward toward the black hole all around where the black hole is. And so if you look at the gas that is blue shifted, well that's going to be the gas back behind the black hole that you observe as being blue shifted as it infalls toward the black hole. Well, light that is reverberating there, well that light has to travel back behind the black hole and then bounce off that and then come back along to reach you, and so that light suffers a longer time delay. Whereas over on the other side, the redshifted side, well that's the side where the infall is closer to you, where the infalling gas is over on the side of over toward you relative to the black hole, so there the lag is much shorter. And so basically, infall produces an overall velocity delay map that broadly looks like this. With the exact extent of it, depending upon the extent of the BLR, it can look like this for a less extended BLR, like this for a more extended BLR. And people have worked out using similar types of geometric and kinematic arguments what an inclined Keplerian disk will look like, what a fixed spherical shell will look like, and what any configuration of matter indeed would look like. And they have then gone and done these velocity resolved reverberation mapping experiments. And you sometimes see systems that look perhaps, at least a first approximation, maybe a little bit like a Keplerian disk, as shown here, or for this one. In other cases, however, here you see what looks like an infall signature, kind of like what is shown over here. Here there might be infall going on. So there might be a significant variety of a phenomenon going on in these broadline regions, and that's worth bearing in mind. Here's another example. This is perhaps the highest quality example of velocity resolved reverberation mapping so far. This is for the very well studied active galaxy NGC 5548, and here you can see velocity resolved reverberation results or velocity delay maps for Lyman alpha, H beta, helium-2, silicon-4, and carbon-4. And broadly speaking, there are a couple of things to note. First of all, you can see that the general BLR response, which is what these color scales show, that general response is largely confined within an expected virial envelope, indicating that the gas is indeed, in this system, bound to the supermassive black hole. Furthermore, then, if you look at the detailed profile here, well, this M shape here looks like the start of a Keplerian disk, and if you model things out and consider the various data quality, and this shows the characteristic shape you might expect for a circular Kepler orbit, the overall inference that comes out of all this is that you likely think that you're seeing a Keplerian disk extending from something like 5 to 20 light days in this system. So in this system, it appears that the BLR may be kind of like a Keplerian disk. Okay, although there are some complexities there which you can read about in the relevant paper. Okay, so now that we've talked about basic observational constraints on the BLR, and we've talked about constraints coming from reverberation mapping, we have to say a little bit about the nature of the broad line region. And as I've already alluded to, there have been many ideas about the broad line region over the years. People originally thought of it as a configuration of clouds. Then they talked about bloated stars and other things, and some people talk about inflow. And by and large, the favored ideas right now go toward, in general, a kind of combination, perhaps, between this accretion disk idea for the broad line region and this outflowing wind for the broad line region, where these two ideas are kind of combined together in a way that I will describe soon. Okay, so those are the various ideas, and some of these ideas have come into fashion and then gone out of fashion over the years. And so to put that into a bit of a human context, I will now show you a famous old plot used by many an AGN astronomer to lighten up their talks with a little bit of humor, and so I can't resist. This plot originally goes back to Dick McCrae, who was a distinguished astrophysicist, a very interesting gentleman. Fortunately, he's no longer with us, back in 1979. And the idea of this plot is it shows the response of astrophysicists to a fashionable new idea. Okay, and so the fashionable new idea is down in here. And many astronomers, arguably the more sensible ones, take note of the fashionable new idea, but they've seen these fashionable new ideas come and go over the years. They take note of it. Their paths exploring astronomy may be perturbed a little bit by the fashionable new idea, but they don't go down too close to it. They take note of it, they consider it in their further work, and then they go about their business quite sensibly. However, there are other astronomers that pass within the accretion radius for the fashionable new idea and are then become enthralled to it. And they orbit around the fashionable new idea, thinking about it constantly. And this region can sometimes become very crowded if the fashionable new idea attracts many proponents. And in this case, in this crowded environment, these attracted astronomers can collide with each other, producing much heat but very little light. So they are radiatively inefficient producers there. And worst of all is the poor souls that fall down through the rationality horizon of the fashionable new idea. These astronomers go beyond rationality and no longer produce interesting ideas, perhaps, because they are fully enthralled by this fashionable idea. And these astronomers down here, notably, even though they're down within the rationality horizon, can continue to emit papers. And the reason for that, and the reason why that doesn't violate causality, is because the papers being emitted contain no useful information. So in any case, that's the response of astronomers to a fashionable new idea. So moving right along, let's again now talk then about what we think the broad line region is like in light of all these data. So we think that the broad line region likely has a sort of composite nature to it. After much research, it is likely that the broad line region itself has a composite nature. To first approximation, sometimes people envision it as having a kind of moderate ionization and high optical depth region and a high ionization and moderate optical depth region. Okay, this is perhaps a first approximation to a more complex truth. This region here, the moderate ionization, high optical depth region, would be largely responsible for the Balmer line emission and magnesium-2, the low ionization lines. Some people envision this as perhaps being the accretion disk itself, or the base down close to the accretion disk of an accretion disk wind. And notably, if you had much of this line emission coming from an accretion disk, well, that could naturally explain the double-peaked line emitters that I showed you earlier on. And furthermore, a disk with a large line emitting region can not only make the double-peaked lines that are sometimes seen, but it can also make single-peaked profiles consistent with most active galaxies. So here, you could have a single phenomenon explaining a broad variety of emission line profiles, both double-peaked and single-peaked lines. So that's one idea. Then there is thought to be another region, again, a high ionization and moderate optical depth region. And this region would be largely responsible for the high ionization lines. This could perhaps be an accretion disk wind. This would help to explain, for example, the blue shifts that are often seen of the high ionization lines, as well as blueward line asymmetries and such. And so to sort of synthesize that a bit, well, the sort of model that many people are partial to, including myself in general, is the one that, not surprisingly, that I showed you when I showed these sort of powers of 10 plots, which again were made by Pat Hall, so he apparently agrees with these ideas broadly speaking as well. So the idea shown here is that the broad line region quite likely has a kind of geometrically thick disk-like configuration. So you have an accretion disk down here. There may be wind material flowing up off the accretion disk. That wind material is irradiated, photoionized by the brilliant central source, and that is what induces this material to produce the line emission. Broadly speaking, that's the idea. And under that general idea, well, then you would expect that the broad line region is roughly equatorial in nature. Some of the lines may be formed down closer to the equator. Other lines may be formed somewhat further up. But broadly speaking, you have a kind of broadly equatorial broad line region. Okay. Many people have investigated these types of ideas. I can't list all of them here, but I refer you to the literature, which is very fascinating, that talks about all of these things. That's the idea, broadly speaking. And then people have, considered the physical processes that might cause the wind to be produced in this region. Here is one interesting model along these lines. There are others as well. But many people have suggested that the line emission may arise in gas that is lifted from the accretion disk by radiation pressure on dust and or magnetic fields. So you have magnetic fields that might be lifting the gas up away from the disk, or you might have radiation pressure on dust lifting the gas up away from the disk. Okay. Then any dust that was initially present that allowed the material to be lifted up off the disk, once the material is elevated up above the disk, and once the brilliant central radiation source can shine ionizing radiation upon that material, well, then that dust is largely destroyed quite rapidly by the irradiation. And once that happens, once the dust has been destroyed, well, then efficient line production can proceed in this material that has been lifted up above the accretion disk. And you get this, again, equatorial broad line region that is dust-free, even though it was originally lifted up from the disk by the dust radiation pressure. It is now dust-free and can thereby produce emission lines efficiently. That's the idea. Okay. And so this is a nice physical model. There's many other details you can read about in this paper and others. And broadly speaking, people seem to be converging toward a general picture like this. Although, to be careful, I would say that there likely are substantial object-to-object variations, with other components often present too. Remember, we see sometimes evidence for infall going on. Okay, so infall sometimes seems to be there to some significant degree. Furthermore, we fully expect there to be stars in this region. Remember, this shows the typical expected density of stars in this region. They're expected to be a significant number of stars in this region. Every once in a while, some stars may get bloated up. Well, they surely should become bloated up by the central radiation source. They may produce a bunch of gas. That may contribute to line emission in some cases. And so much of the sort of object-to-object complexity that we observe, particularly among notable extreme objects, can be understood by these varying other components coming into play to significant degrees in some systems. But broadly speaking, if you had to consider all of these ideas, in general, the favored ideas right now are the kind of a combination of the accretion disk and an outflowing wind, producing this equatorial structure that, again, is stratified with different lines being produced in somewhat different locations. And that is thought to be, according to our best understanding right now, the general nature of this broad line region.